And okay, we're recording now, so you can go ahead whenever you're ready, Brian.
All right, well, welcome to Cafe Scientifique. This forum is designed to bring science into the community. And the idea is to provide a relaxed setting for people to learn and talk about current scientific topics. So kind of the format for this evening is we're going to have a presentation, and then we'll follow that with a question, answer, and discussion session. So please just sit back and enjoy this first part of the evening, and then please join in with Q&As. And if you're not familiar with the Zoom platform, you'll see at the bottom you should have a little Q&A button, so you can type your questions in there, and you don't have to wait to the end. If you have a question and you want to just type it in, you can put it in as soon as you think of it. So this Cafe Scientifique is actually funded by the Montana Idea Network of Biomedical Research Excellence, or INBRE. And this is actually part of your federal tax dollars at work through the National Institute of Health. So INBRE is a network funded by the NIH. So I'm Brian Bothner. I'm a faculty at Montana State University, and I'm the director of Montana INBRE. And so at the INBRE, our goal is to essentially enhance the research capabilities and the biomedical workforce pipeline here in Montana. So we're working with institutions all over the state, working with funding research projects and prioritizing student development, with trying to essentially deal with health equity issues across the state of Montana here. So as we've seen, we're all getting used to this, virtual format. While there are a number of drawbacks, we don't get to, really look each other in the eye, and we don't get to talk with each other. There are some benefits because we have people from Alaska, Florida, California, Minnesota, Canada, all on board this evening. So that is nice to see that we're able to, bring in people, and we're also able to spread messages more broadly with this approach. So, we're certainly hoping that we get to go back to a live format for this, but for now, let's just sit back and enjoy it. And our last Cafe Scientifique was put on by Dr. Helen Mayberg, and this, was definitely a success, and we had a wonderful discussion afterwards. So, we're looking forward to that same event this evening. So I'm really pleased to introduce our speaker tonight. So Dr. Dave McWethy, he's an assistant professor in Montana State University's Department of Earth Sciences. So McWethy earned his doctorate in ecology and environmental studies from MSU. And his primary research interests include understanding ecosystem diversity, exploring mechanisms driving changes to Earth's vegetation, and developing a framework for understanding ecosystem vulnerability to human activity and climate change. Dave has published in nearly all of the top scientific journals. He is very well published. He actually leads research projects also all around the world, from Italy to Australia and New Zealand, some of the places that he's worked. He's also a member of MSU's Paleoecology Laboratory, and you may have seen that he was recently featured in a New York Times article examining wildfires in the Western US. And that kind of arrives us at a topic which I know is really, I don't want to say dear to all of us, but something those of us living here in the West and in Montana really think about are wildfires and their impact not only on the land but on human health. There's a big impact there. So with that, I will turn this over to Dr. McWethy.
All right, thank you very much, Brian. I'm going to share my screen here. And can you see that, my first slide?
Looks good.
Okay, great. Thank you for that introduction. And I'm really pleased to be invited to participate in the Cafe Scientifique series. I think it's a great series, and this topic is certainly one that is spurring a lot of discussion. And so I'm going to touch on a lot of things in my talk, and I'm going to leave a lot to discuss. So I'm really looking forward to the discussion at the end as well. And I just want to start out acknowledging that the lands that MSU lies on and a lot of the places that I work in Montana, in the West, and around the world are places that indigenous peoples have been inhabiting for thousands of years. And I've had the great fortune of working with many of the tribes in Montana on my research and really learning a lot from the vast knowledge, traditional knowledge that these tribes hold and are passing on. And a lot of this is really something that can help us learn to live with fire in the future. And so I won't read this, but I want to acknowledge the lands of the Gallatin Valley, of the Valley of the Flowers. And some of the pictures here, some of the students that I've worked with from tribes around Montana. So the 2020 fire season was truly remarkable in the West. We had so many record-breaking events. We had over 23 megafires, which is something that we actually didn't really talk about a few decades ago. While we might have had a few megafires, fires that are over 100,000 acres, fires that cost a lot of money and cause a lot of damage. This year we had over 23 in the Western states. And while Montana had somewhat of an average fire season, the rest of the West really got hit hard by some record-breaking fires. And we did have right in our backyard here, the Bridger Foothills fire, and I'll talk a little bit about that at the end of the talk. So I'm going to first touch on how we know, what fires in Montana were like in the past. I'll talk about the 2020 fire season and some of the main factors that led to this fire season. We'll talk a little bit about the Bridger Foothills fire because it was one of the recent fires that we all got to see destroy quite a few homes and structures and threaten a lot of folks in the valley. And then I'll talk about what's projected for the future, and I'll just end with some ideas for how we might better live with fire into the future based on these projections. So in the spirit of Cafe Scientifique, I thought I would just spend one moment talking about how my interest in fire started. And while I think I've always had some interest in fire as a process on Earth, when I went to the Peace Corps in Senegal, West Africa, this is a photo of some fires as I was flying into Senegal. And it's this kind of was all over the country when I came to Senegal. And when I came out to my village, the Peace Corps, and I'd gone through a couple months of training, and I was an agroforester volunteer. And a lot of our training focused on enriching soils, composting, doing these large pit composts. And one of the main thrusts of our training was to try to prevent fires and get some of the people, the communities that we're working with to reduce intentional use of fire. And so I came to my village and, spent a lot of time listening, observing, but also talked with the family I lived with and the folks in the village about reducing their use of fire. And And this was a crazy idea to folks. And at first from my training, I didn't quite understand why, but after I was there a few months, I realized that the idea to not use fire to prepare lands for growing food and safeguarding the community from a lot of the critters, snakes and hyenas, and a lot of the things that people need to see when they're out. A lot of the agriculture that was being done was in these kind of open forest environments with a lot of grass, this tall grass, as you can see in the slide. And I learned very quickly that not using fire was a very dangerous proposal. And while I understood that the Peace Corps' mission to try to improve soil fertility, fire was an integral part of the way people prepared land and really protected their communities and lived in a very harsh setting. And so I was fascinated by how fire was used and how powerful a tool it was, and how it really benefited communities and in many ways the ecosystem, depending on how it was used. And walking out in the bush in Western Senegal or Eastern Senegal, I also became very positive to the role of fire to safeguard myself from snakes and other things. You could see them much better, and they would kind of drift off in areas that had been burned. So I gained a great appreciation in many different ways of the use of fire, and this grew over the years, especially when I started working with other indigenous populations around the world, in Tasmania and Australia and New Zealand and Patagonia and in the Western United States, among other places. So that's just a little nugget about how I kind of got a passion, interest in fire. And before I kind of move on here, I also want to acknowledge the Paleoecology Lab that Dr. Kathy Whitlock started several years ago, and she spent decades and decades working in the greater Yellowstone area in the Western US and also around the world, looking at fire as an important disturbance and process. And the graduate students that are currently in our lab, I couldn't show all the students that have been in the lab over the years, but these students are really providing the valuable research and time and effort to help us learn about fire and adapt to fire into the future. So the first point that's very important to start off with is that fire is a natural disturbance that has shaped the Earth system for over 400 million years. As soon as there was enough oxygen and fuel on Earth to burn, we had fires, and it's shaped the diversity of life on Earth. When we talk about modern ecosystems, fire provides diverse landscapes of young and old forests and different types of grasslands and woodlands, forests of different species and diverse habitats for wildlife, and really a lot of different resources. And without fire, the Earth's diversity would certainly be much less, and the types of habitats we would have would be less. A lot of plant and animal species are well adapted to this process that shapes the Earth. And if you take a look at satellite imagery of fires on Earth, really in any month of the year, you can see how important this process is in shaping vegetation and ecosystems around the world. Here's a snapshot from a few years ago in September, and this is not unusual. You see this kind of broad brush of fire that shifts seasonally in the northern and southern hemisphere. And it just, when I first saw these images, it really kind of strikes, a strong image of how broad and how wide a swath of fire affects in any given year. This is certainly true for the Western United States. And I just have two panels here from Pat Bartline showing lightning-started fires over a decade on the left panel and human-started fires over the same decade. And if you look at the pattern of these fires, you can see that there's quite a bit of overlap. But there's some areas where human-started fires fill in where lightning is not naturally frequent. And if you look at the timing of fires, we certainly set fires during times of the year where we wouldn't see a lot of lightning. But the point here is that we have a lot of fire in the West, both naturally lit and or started, and also from human ignitions. The fire ecologists love these fire triangles, and they really help us understand what factors drive all aspects of fire, from just a flame, where of course we need oxygen, we need heat, and we need some type of fuel to have a flame. When we start talking about an individual fire, the factors that drive that fire and that fire's behavior are weather and topography and the type of fuel and its abundance and continuity. And when we think of a fire regime, this is the pattern of fires that we have across a landscape over many years and decades. The factors that influence fire activity are climatic conditions, both extreme and average conditions, the type of vegetation and how abundant that vegetation is and how continuous it is, and then both natural and human ignitions. And today I'm really going to focus on this fire regime triangle. And the reason I'm going to do that is because understanding these three main factors really helps us understand what has happened in the past and what we should anticipate for the future and prepare for the future. And also understand what happened in 2020. So climatic conditions, we'll take a look at how those influence fire activity, the type and abundance and continuity of vegetation, and both the role that human ignitions and natural lightning ignitions play. And all of these are interacting to shape landscapes in the fire regime. So in Montana, when we think about how these three main factors interact, we can talk just briefly about how they shape the landscapes that we see, from grasslands to open forests to our dense lodgepole forests, which are pretty common in Western Montana, to our subalpine and alpine forests. We have quite a diversity of fire regimes in Montana. In our grassland systems, these would naturally experience frequent surface fires. We call these low severity fires that roll around along the surface, burning the grasses. And prehistorically, we would expect these types of fires in grassland systems to occur as frequent as every year to every couple decades, depending on the system. In open forests of ponderosa pine and Douglas fir, we have quite a diversity or range of types of fires that can occur. We can have these surface fires that run through the brush and the grasses that don't kill the trees, that occur more frequently, as frequent as a few decades. And then occasionally we'll have a hotter fire because of extreme weather conditions that will jump to the canopy and result in more tree mortality. And these are less frequent, occurring, as infrequent as a couple hundred years, once every couple hundred years. And in these open forests, which are quite common in parts of Western Montana and Central Montana, you can have surface fires and canopy fires occurring almost in the same place. So they're quite diverse systems and diverse fire regimes. In our dense lodgepole forests, really the natural fire regime is one of an infrequent yet very severe and high mortality type fires that occur once every couple hundred years. This is changing a little bit with the type of rapid climate change we're experiencing, and I'll talk about this later, but the natural fire regime in these dense forests are really these infrequent but severe fires. And this is similar for our subalpine forests higher in elevation. So how do we know about past fires and past environmental conditions? In the paleoecology lab, we go to lakes. And in this wonderful photo here of a lake nestled in Alaska, surrounded by a recent fire and some fireweed, all of these wonderful materials that occur during a fire and just during the normal growth of the ecosystem, pollen and charcoal and needles, they get deposited in the lake and they provide a record of what happened in the past. So we can go to these lakes. Here's a lake in the Mission Valley in northwestern Montana. And we obtain these sediment cores that in these systems, they are laid down over the years in a chronological order, and it can provide a wonderful history of what happened in the past, both with fire activity and vegetation change and also climate change. So we can look at, we can look at the charcoal and the pollen. We can look at tephras, volcanic eruptions, and all the changes that are documented by the different strata in these cores, and we can reconstruct what happened. I'm just going to show you one example of a paleoecological record from one of our graduate students, Pico Alt. She cored Twin Lake in the Mission Valley in northwestern Montana. And she, I think this was about 5 to 6 meters of mud from the center of Twin Lake. And this figure here, I'm just going to orient you a little bit here. I'm not going to show a lot of data in this talk, but I wanted to give you at least one example. On the bottom, on the right, is 15,000 years on the x-axis and present on the left. So if you go from the right at the bottom to the left, you're going from 15,000 years ago to present. And the bottom panel shows how much charcoal that we recorded at this lake over time. The next panel up, the black line, shows how fire frequency changed over the last 15,000 years. And then the blue, the green, and the brown lines show how 3 of our kind of indicator pollen and species or groups changed over the last 15,000 years. So spruce pollen was very high coming out of the last glacial around 15,000 years ago. And this decreased when things became quite warm in the mid-Holocene between 11 and 7,000 years ago. And then when things cooled and got wetter, it increased again. We see the opposite with Douglas fir on the green line. Douglas fir does well when it was warmer and drier. And the same with grasses. We see more grasses during that warm and dry period. We have a whole suite of different species that we look at with the pollen. We compare that with the charcoal. We compare that with independent climate records. And really, when we put sites from all over the Western United States together and the Northern Rockies, we can look at dozens and dozens of these sites. And the take-home message is that all of these sites, all of these landscapes, especially in forested systems, they experience a lot of fire activity. Since the last glacial, there's been fire activity across these landscapes. And the ecosystems have responded very dynamically to both the climatic change and changes in fire activity. The general trend that we see is that during the mid-Holocene, where we have warmer and drier conditions across the Western US, we see more fire activity in forested systems. As things cool the last couple thousand years, we see a decrease in fire activity. And that I'll talk a little bit more about that basic relationship between temperature and fire in a minute. So we can put all of these paleoecological records for the Northern Hemisphere together on the upper panel here. And this time the x-axis is 22,000 years on the left ago and present on the right. And if we put all of the charcoal records together for the Northern Hemisphere, we can see, if you follow this blue and black line, that coming out of the last glacial, we don't have a lot of fire activity, and then it increases dramatically and then kind of plateaus out over the last several thousand years. Why is this happening? Well, our Greenland ice core temperature reconstructions show that it's really following temperature and also fuels coming onto the landscape. I don't want to get too complicated with this data, but the basic message is that when we came out of the last glacial, we started having vegetation grow where ice used to be. And you had grasses and tundra vegetation, and then forest vegetation started to spread. And as you got warmer temperatures, we had more fire. And that's a really important relationship that is relevant today and will be in the future in forested systems. So we'll come back to that at the end of the talk. I'll give one more example about Yellowstone, because most of us are familiar with the 1988 fires in Yellowstone that burned over 700,000 acres. Kathy Whitlock and some students in the paleoecology lab did a really nice study. Phil Higuera, who's at University of Montana, looked at the size of fires, how much biomass was burned in the Yellowstone area over the last several hundred years to try to get an idea of how unusual the 1988 fires were. And the basic take-home message is that every couple hundred years, you see really large fires in Yellowstone. So these are not unusual patterns for these lodgepole pine systems to accumulate a lot of fuel, become quite dense, and then when climatic conditions are right, when you have really hot, dry fire season and the right ignition for fire to spread, you get a very large area of Yellowstone burned. The 1988 fires were still exceptional in that they were a bit higher in magnitude than is recorded in this paleoecological record, but it's not unusual to have these really large events every couple hundred years. So we learned a lot from this kind of historical record. The general trend over the last 2,000 years, so 2,000 years ago on the left and present on the right here, is we had this long-term trend in cooling in the Western United States, followed by the little ice age, which is a little dip for a couple hundred years. We had generally cooler than average temperatures, and fire activity followed this cooling trend until Europeans started colonizing the Western landscape and deforesting and burning the landscape. We had a huge increase in fire activity in the early 20th century, especially in the Pacific Northwest. That really coincides with clearance of the land for European settlement. That was followed in the 1930s by an incredibly effective fire suppression strategy that essentially eliminated fire from a lot of Western landscapes until, even now, in a lot of cases, for the last several decades, we've really reduced the amount of natural fire activity that's occurred. Now, when we think back to that relationship between temperature and fire activity that we know is very strong in the historical record, all the models show with our current climate warming that we're experiencing, we should be seeing an exponential rise in fire activity. And in that, the 2020 fire season is something that's quite in line with what the models were projecting a few decades out. So that simple relationship between temperature and fire activity is something that we're not going to be able to avoid. And I think that's one of the main factors I'll talk about in terms of why we had so much area burned in the 2020 fire season. So the main lessons from the historical records that we work on in our lab is that first, that fire is a natural disturbance. It's shaped ecosystems for millennia in the Western United States and around the world. That this very simple but strong relationship is very apparent in all of our records, that when we have warmer temperatures in forested systems, we get more fire activity and more area burned. And also that the patterns and the frequency and severity, all the characteristics of fire, different fire regimes, they vary across ecosystems types. So our records from grasslands systems are different than those in our forested systems. So I'm going to shift gears here and talk a little bit about the record-breaking 2020 fire season that affected so much of the Western United States, and also Montana, with a lot of the smoke that we experienced. Over 8 million acres were burned. Again, we had those 23 mega fires. A lot of those mega fires were in California, 7 in Oregon, 4 in Colorado, the largest fire in Colorado's history, the Cameron Peak Fire, 3 in Washington. We lost many lives, and many buildings were lost, including over 60 just from the Bridger Foothills Fire. In California, the top 5 fires in the history of California occurred in 2020. All of these were over 300,000 acres. So these were quite remarkable fire events. And if we think back to that trend in fire activity, again, the models project on this right panel here, this exponential increase in fire activity, and we've largely escaped that until 2020, which is really off the charts, but that's something that the models are projecting for an average fire season. So it's something that we really need to be aware of. So there were so many records that were broken in 2020. Here's an image of a pyrocumulus cloud from the Cameron Peak Fire in Colorado. Again, this was the largest fire ever recorded in Colorado's history. This pyrocumulus cloud reached over 40,000 feet in the atmosphere. And when these types of events start ejecting ash into the atmosphere at those elevations or those altitudes, it's truly a global event. And NASA was able to identify smoke from the Cameron Peak Fire covering a large section of southern Italy. So these are truly global events, and they're affecting people around the world in terms of their impacts from smoke. The Cameron Peak Fire also had smoke-nado, some of these really extreme fire behavior events. Several of the California fires had these really large firestorms and pyrocumulus clouds that are really challenging for anybody to consider in the firefighting context. It's something you just need to stay away from. As Brian mentioned, fires have a lot of health effects, and you can see from this image, this satellite image of aerosols that are traveling across the entire United States. These are all originating from the fires in California, Oregon, and Washington, and they're traveling all the way to the eastern United States. And again, like I said earlier, the Cameron Peak Fire traveled all the way to Italy and in Europe. So the air quality impacts are really significant. And just a snapshot from September 9th, here's an air quality index, the PM 2.5. This is fine particulate matter that is less than 2.5 microns in size, and this is charcoal or soot. And the problem with this size of soot is that our body has no way to protect itself from these small particles. Particles that are larger than 2.5 microns, we can usually protect ourselves through mucus and ejecting that material, but these really small materials, when we inhale these into our lungs, we don't have protection. So it's very unhealthy for humans to really be exposed to this particulate matter for long periods of time. And I mean, there's some interesting correlates here with these different colors. So if it's greater than 150 PM 2.5, it's like smoking 10 cigarettes a day. Over 200, it's equivalent to smoking 14 cigarettes a day. And over 300, it's equivalent to smoking 22 cigarettes a day. And some of these numbers for September for the megafires that were occurring in California, Oregon, and Washington were over 900. So you can see that the scale and the legend stops at 500. This product that is provided only records up to 500, but some other registers were showing that we're almost reaching 1,000 from these fires in 2020. So the health impacts are really significant, and it's something that we need to prepare for in the future to protect our communities. So I'm going to return to the fire triangle for the fire regime to really look at what were the main factors that led to these extreme fires and the high number of megafires that we had in 2020. And the first and the most important is that we had this climate-enabled fuel drying. And this is a long-term trend that we've had for a few decades now. And this is something that's not projected to change. Essentially, it's that warming temperatures, despite in some cases increases in precipitation, increases in temperature are drying fuels out at a very large scales and providing an explosive situation for fires to spread. We also had some unusually strong winds this year that were somewhat specific to this fire season. We had an unusual lightning event in California, which I'll talk about in a minute. And then we have a long-term trend of humans adding ignitions in the wildland-urban interface where they would naturally not occur. And this trend is very something that we should pay a lot of attention to, because it's also fueling these really large fires in places where we don't want them. And then lastly, I think this gets a lot of discussion. We have accumulation of woody fuels, especially in our dry forests in the West. But I think a lot of the discussion focuses on this fuel accumulation when it's actually one of the minor components of why we had such a large 2020 fire season and why we will have large fire seasons in the future. It's something that is contributing, but it's not the main reason why we're having such large fire events. So I'll start with that. We have had since the era of fire suppression in the 1930s, that started in the 1930s and has persisted until today. A lot of our forests, our dry forests in Montana and throughout the Pacific Northwest, kind of looked like this, which is an image of a forest in Western Montana. And today they look more like this. These are actually photos that were taken from adjacent forests in the Blackfoot Valley in Montana. The right being a forest that we can see a lot of these ladder fuels, these smaller firs have been growing in and becoming more dense. The forest on the left was actually restored to what the historical records suggest it looked like prior to the 1930s. And so in these dry forests, we can see we do have quite a bit of fuel accumulation, and that is true for a large number of the dry forests in the Western US. So we have more abundant and connected fuels. We'll move on to climate, this climate-enabled fuel drying and the strong winds. So early in the fire season in the Southwest, we had record-breaking vapor pressure deficits, which is essentially dry atmosphere. It's atmospheric, it's a measure of atmospheric thirst. So this just sponges all of the moisture out of the soils and out of the atmosphere. And the Southwest experienced this extreme low vapor pressure deficit in the early spring or throughout the fire season. And then in the interior Rockies, southern and northern Rockies, just another measure of atmospheric thirst or evaporative demand drought index, we again broke records throughout many of the states in the Rockies in terms of our measures of atmospheric thirst. So the dry conditions that we experienced in both the spring and the Southwest or throughout the fire season, and then later on in the northern and southern Rockies, were record breaking. And this really prepared all of these fuels to burn once there were ignitions on the landscape and high winds to fuel those fires. We had this somewhat uncommon easterly wind event that drove a number of these mega fires in Oregon and California. And what's remarkable about these fires is that a number of these were just 10 acres, 20 acres in size until the easterly winds blew them into over 100,000 acres in just a matter of a day or two. That is really unusual fire growth. And that's some of these were unprecedented. And I won't get into the big details here in terms of the synoptic climate, but the main reason we have these easterly winds is we had a cold front push down from Canada actually into Montana, which prevented us from having the worst of the easterly winds, at least where we are in Bozeman here. And the pressure difference between that cold front and the pressure system out in the Pacific resulted in a 100-mile-per-hour plus winds, easterly winds that really fueled these large fires in Oregon and California. So this was somewhat of an unusual fire event, but we've seen in some of the largest fires in the Pacific Northwest, the Yakult fire, and others, we've seen an easterly wind component that has driven those large events. We also had this unusual lightning event, and then this long-term trend that we're adding ignitions in the wildland urban interface. So in California, these purple dots represent lightning strikes. And on August 15th, last year, we had almost 5,000 lightning strikes in one day. Just a day and a half later, we had over 7,000 lightning strikes in Northern California. And when you add, just imagine adding almost 10 or over 10,000 lightning ignitions on top of those extremely dry fuels. So we had record-breaking atmospheric thirst or dry conditions, and then you have these lightning strikes essentially all over the Californian landscape. And then the easterly winds. So it's a recipe for very large fire growth. So this figure shows, I'm going to start with the right-hand panel here. This is natural ignitions from lightning in any given year. You can see that we have a wide distribution of natural lightning strikes throughout the United States. But if we look at human ignitions just in the wildland urban interface, these are all new ignitions that we're adding in places where there's plenty of fuel to burn, but it's also where people are living. And these are ignitions that would not naturally occur. So we're adding a lot of ignitions in places, again, that we don't want them. And the other trend that, goes along with this is that the growth rate of homes in the wildland urban interface is growing extremely rapidly in the Western US. So not only are we adding ignitions, but we're moving to these places where there's fuel and we're adding ignitions. So to summarize, it's fairly simple in terms of the factors that led to the 2020 fire season. It really comes down to the fact that much of the West the fuels were dry. We had warm temperatures and a dry atmosphere, and it really sucked all the moisture out of the fuels, preparing the landscape to burn. We had abundant fuels, and we're adding ignitions where people are living, especially in these new places where we're moving, the wildland urban interface. So I'll shift gears and talk a little bit about the Bridger Foothills fire. I'm sure many of you saw this and witnessed this last September, and it was quite remarkable and scary fire being so close to our homes and our community. The investigation showed that a fire from a lightning ignition was smoldering. It could have been as early August from a lightning strike. And that smoldering ignition blew up on September 4th in the afternoon with some relatively modest winds just to the northwest of the M. There was an amazing firefighting effort, and all of these aircraft, I did not take these aircraft from different fires. I didn't take these photos, but all of these photographs were taken of aircraft that were used to fight the Bridger Foothills fire on that Friday, September 4th. And I'm amazed by the number of aircraft and the amount of resources that were used to try to put that fire out. And of course, there were a lot of people that were put on the ground to also put that fire out. I think, they made quite a big dent in the fire by Friday night. But during the night of September 4th, the fire did move over to the east side of the Bridgers, as is evident by this photograph. And then the fire blew up midday Saturday, September 5th, and it had only really covered a couple hundred acres until it blew up in the middle of the day and quickly spread to 8,000 acres in a matter of hours. And that's when most of the structures were lost. If we look at some of the weather conditions during the fire, we had plenty of, this is from the Ross climate station in the Crazy Mountains, so not too far away. We had temperatures over 80 degrees, so quite warm, wind gusts of over 50 miles per hour, very low humidity, less than 10%. And we really hadn't received any rain for many days. So we had all the conditions for a fire to spread and grow quickly. I think what's remarkable for me is that while all of these conditions, warm temperatures, high wind gusts, low humidity, and really lack of rain, they certainly came together to I guess, provide the conditions for this fire to grow quickly. If you look at the data for any August or September in Southwest Montana, these are not unusual conditions. So the message that I take is that, we're often lucky that we don't have fires take off like this, like we had with the Bridger Foothills fire. We certainly have the conditions for this to happen again. And I want to just, I show this image because I did hear in just talking to people in the community, some people mentioned that they thought that the firefighting effort was less than they would have liked to have seen on Saturday. And I think of this image, this is a plane in front of the Bridger Foothills fire smoke plume. And you think about the scale of this event that was happening in the middle of the day on Saturday, and how many planes would you need to try to put this fire out? And so it's an important thing to remember, that the scale of these extreme events, they're very difficult to manage as firefighters. There were quite a few areas in the Bridgers that were burned severely, and by severe, I mean high tree mortality. So here's a photo of the Newhall Ranch that folks have generously allowed MSU researchers to start some monitoring of the post-fire conditions. And if you look at this map, preliminary map of fire severity, you can see the kind of backbone of the Bridger range in the kind of center left here, the M down here where the fire started. The red indicate the high severity areas. So much of the fire was actually low to moderate severity in terms of the effect on forest vegetation or vegetation. Many of these areas should recover quite well, especially the yellow and orange. So the last part of my talk, I'll just touch on some of the projections for the future for Montana. And the main trend that we're seeing that's very consistent and strong throughout the state. So this is a temperature change from 1950 to I believe 2016. And each of the panels represents a different region of Montana. And you can see, while there's some year-to-year variability, the trends for all of the regions of Montana show an increase in temperature, and that generally is around 2 to 3 degrees Fahrenheit increase over the last 30 years. The warming is occurring greatest in the spring, and maximum and minimum temperatures are both increasing pretty significantly. If we look at the climate models, so this is out to 2040 to 2069. There's 3 different models that I'm showing here. In the top row are temperature models, and they all show upwards of almost a 10-degree increase in temperature for a good chunk of Montana, all 3 models for the summer, June, July, and August. So that's a very dramatic increase in our average temperatures for the summer season. And you can see that all 3 models are fairly in agreement, or fairly consistent in their projections. If we look at the bottom panel, this is for precipitation. And again, this is for June, July, and August. And we can see that the left model shows a potential increase in summer precipitation for Southwest Montana. Most of Montana being fairly showing a slight drying. The other models show a very significant, or the right model here showing a very significant percent change, upwards of 30 to 40% decrease in precipitation for summer. Our confidence in what's going to happen with precipitation, as indicated by these models and others that we look at, is fairly low. We're not sure exactly how much precipitation we're going to get in the future in the summer. But what's really important to remember is that even if this left model on the lower left corner here is the right model, given that we have a slight increase in precipitation in the summer, a 10-degree warming is enough to very much overcome that slight increase in precipitation in terms of drying out the system. So we're really anticipating is a much drier system in our summer seasons in the future. And one of a real striking image that Leroy Westerling from University of California, Merced, who's been doing quite a bit of research in the Yellowstone area, shows this image of the moisture deficit in 1988. Again, this is similar to vapor pressure deficit. It shows atmospheric thirst and essentially fuel drying. And these were the conditions in 1988 on the left panel. And the projected moisture deficit for 2090 is much more severe. And the average conditions that are projected for the future are really expected to be worse than what was in place during the 1988 fires. So our average conditions are going to be quite dry. And when we think about how big the 1988 fires in Yellowstone were, again, it's another reminder that we should be prepared for larger fire seasons. Just an image of the number of weeks with a risk of very large fires. And this is again for the future, for 2040 to 2070. And you can see in Montana, we're talking about 500% or 600% increase in the number of weeks of very large fires. And I'm just going to return to this basic relationship between temperature and area burned that is very evident in our paleoecological records. It's really what we should expect. There's all of the models and all of our historical records and what we're seeing in even the last few decades suggests that with warming temperatures, we're going to get more area burned. And one model suggests that we're going to get over a 1,000% increase in area burned in just a couple decades. And we see a number of research efforts that are showing similar projections for Montana and the Western US. In terms of ecological implications, I'll just hit on one, and that is some researchers, a large team of researchers have found compelling evidence from a number of sites throughout the entire Western US, showing that in drier systems, when we have fires, we're not getting forests returning. The post-fire conditions are warmer, the soils are drier, and the seedlings are not getting established. And I just want to emphasize these are in drier settings. So you could think of the Bear Trap 2 fire, the Bear Trap Canyon fire, and some of the lower elevation fires in the Paradise Valley. In these drier sites, we're not seeing a lot of forest regeneration. And that's something that we're seeing throughout the Western United States. So we are likely to see this transition of these drier systems that were forest to grassland and shrubland systems. The wetter forests at higher elevations, we are seeing these forests recover to forest systems after fires. So the important lessons that we can learn from our historical records and the 2020 fire season and the factors that are driving large fires. First of all, again, I'll return to this important concept that fire is a natural disturbance. It's been around for millions of years. It's an important process that promotes diversity. And many species are well adapted to fire as a disturbance. This relationship between a warmer climate and more fire activity is very basic at large scales, and it's something that we should expect to continue in the future. There are three main factors that are promoting increasing fire activity. There were the same factors that promoted a lot of fire activity in 2020, and these are a warming climate, abundant, well-connected fuels, and humans adding emissions to the landscape, especially where humans live. So I'll end with this last slide, and I just want to, this is really, I think, a remarkable image in terms of the message that it sends. This is from the management of the 2017 fires in the Western United States. Each gray block represents 10 fires, And the red blocks or squares represent fires that were allowed to burn without full suppression efforts. So one of the main things that we're learning from research on fires and how to minimize the most destructive fires is that allowing fires to burn is one of the best treatments in safeguard. Fire itself is a great way to protect our communities. If we can allow fires to burn when they're not dangerous and during the times of year where they're not going to spread into the mega fires. So one of the things we have to address is this kind of historical legacy of fire suppression that is evident in this image. And some of the main messages that fire ecologists are really trying to communicate is that first, acknowledging that fire is inevitable is the first step for our communities to really prepare to adapt to fire in the future. If we really want to avoid this increase in these mega fires, we do have to slow climate warming, and that is something that we can't really escape. We can start to prepare and adapt for large fires, but if we don't want the worst fires to happen, we have to start to slow climate warming. We should adapt and prepare and adapt to more fire. And we know as fire ecologists that allowing for more but less severe fires is really a way to safeguard communities and ecosystems as well. And lastly, and I think all of these can be points that we can discuss. I'm sure folks will have a lot of questions on these. But the last one is to fire harden the home ignition zone and really take care of the home environment to reduce the chances that your home can be ignited if there's a fire in the surrounding landscape. And there's a lot of great material that Headwaters Economics here in Bozeman has communicated and is available through their research. So I want to thank everyone for the time to start off this presentation, and I'm really looking forward to the discussion. So I'll kind of hand it off and prepare for the discussion part of the talk.
Thank you very much, Dave. That was really riveting. Yeah, and it's just, I was really struck by, some of the picture of the plane and the cloud. And just, it really puts the scale of these events in perspective. And once you get these mega fires, it seems like there's just nothing you can do. I mean, they're in control.
Yeah. Yeah, and I'll respond to that. A lot of fire ecologists have posed the question that for some reason, we treat these really large fire events different than we would a hurricane, something that we wouldn't think about trying to fight. And I think we should start thinking of at least certainly these mega fires as processes like hurricanes that we really shouldn't be trying to fight because the scale is just too large, at least when they get to that extreme situation.
Yeah. All right. Well, so we have some questions coming in. And so one that came in earlier, and I think this is, maybe a lot of us that live here in Montana and other communities are thinking after this is, what are individual Montanans and communities to do to protect themselves as we think about this?
Yeah, well, that's a great question. And we spent a lot of time thinking about this question. And the first thing we did is we tried to find communities in the Western US that have experienced multiple fire events. And, we're kind of forced in many ways to try to prepare for those to happen again and adapt. And we found some really good examples of communities that have, essentially embarked on a multifaceted approach to adapt to future fires and to safeguard their communities. And every community was different, but some of the main elements include acknowledging first that fire is an inevitable part of the landscape. That's the Montecito Fire Protection District in California was one of the best examples that we found. And they have a great kind of outreach and education program saying, look, we cannot escape the fact that we're going to have another fire affect our community. So how can we prepare and help protect people? So that was the first part of their kind of campaign. And then the second part was that they had people really look at their home ignition zone. So, there's different levels, but there's the immediate home, what your home is built of, what kind of windows do you have, what kind of roof do you have, siding, and what kind of fuels do you have around the home environment, and how can you reduce fuels around the home environment and change the type of material your home is built with, so that if there are embers that are landing on your roof or being sucked in your soffit, how can you prevent those from getting inside the home to ignite the home? There's a number of fairly simple things people can do to actually protect the home environment, and then start to move out. So they have these different zones, 10 yards from the home, 20 yards from the home, and 30 yards from the home. And there's a lot of great resources out there to help people remove fuels and change their home environment so that they can reduce the chances that their home will actually ignite if there's a fire in the area. Yeah. So that's kind of the second, or I won't prioritize these, but that's one of the other components, is to protect your home from igniting if there's a fire. And one of the key ideas there is that embers from a fire can travel upwards of 1 to 2 miles in front of a fire. So even if a fire is a mile or two away, a lot of homes are actually burned because embers get sucked into the soffit of a home and ignite the home from inside. So these are simple things that you can do, that if embers are traveling out in front of a fire and they land on your home, that it's not going to start your home on fire. The other big part of these communities that have been successful and better preparing for fire are to start to think about fuels around communities. And, as fire ecologists, it's really important that we communicate that, a fuel is anything that can burn. And in the Tubbs fire and the Santa Rosa fire in California, homes were actually the fuel. So people often think of a pine forest or a coniferous forest as being a real dangerous fuel source. But if you think of anything out there that can burn is a fuel. And so, thinking about the fuels that are around communities and changing those so that if there is a fire, communities and firefighters have a better chance of managing those fires to protect people. And it's very difficult to prevent fires from occurring in a lot of the Western landscapes, even if they're not forested systems. There's plenty of grass, there's plenty of shrubs, and all these can burn, and even homes themselves, like I said, from the California example. So in the case of the Montecito Fire Protection District, they had a free program, they still have one today, where you can remove fuels around your community, woody fuels, and they'll come and pick those up. And they're trying to remove a certain density of woody fuels as a buffer from the more remote forested landscape. The last kind of component is using prescribed fires as a treatment itself, and allowing natural fires to burn where you can do that safely. And so applying prescribed fires typically happens in the shoulder seasons of the fire season. We call it the cool season. So in the spring, the early spring or late fall, applying prescribed fires to the landscape removes a lot of the fuel that would result in a very severe and damaging fire. If you do that, it doesn't mean fires won't come into the landscape, but it means that they're much safer to manage. So I guess those are some of the big examples, and there's about a 20 more, but each community that we looked at, the Methow Valley in Washington is another community. They have kind of assembled a suite of approaches that is helping to safeguard their communities. And those are some of the examples. I could go on, but maybe I'll stop there.
Yeah, we have questions in a number of areas, and I want to come back to that safety thing. But speaking of this planning, I think what many of us here in the Bozeman community are aware of the kind of plans for the highlight area and the fuel reduction in there, I guess. So one of the questions is, what are your thoughts on that management plan? And
yeah, excuse me. Yeah, I had one of my classes look at that plan, and we actually met with the Forest Service, and I think one of the challenging things about that plan is, the objectives. There's different objectives for that plan, and one of them is to protect our watershed from a large post-fire debris flow. Now, I understand that we do not want to have a big debris flow clog up our water supply system. We don't have a lot of reserves, and so I think it's an objective that is worth considering, whether you're able to reduce the chance of a large debris flow from occurring is quite a challenging effort. And the reason is that what you're aiming to do with a fuel reduction or a fuel management project is you're not trying to stop a fire from occurring. You're trying to stop the type of fire that occurs from a high severity fire, a canopy driven fire, to a low severity fire. One that would have much less chance that you'd have a big rain event or some kind of storm event that would result in a big debris flow. If you look at the plan, I think it makes sense. I mean, they're trying to use a number of different approaches to reduce the chance that you get a really high severity fire in the highlight watershed that would result in a post-fire debris flow. You would have to maintain that type of system every 10 to 15 to 20 years. You'd have to go back in and remove fuels pretty frequently in order to do that. And I think, if the main objective is to protect the water supply, trying to do that right around where those water systems from highlight are entering the water treatment plant makes sense. Now, it's not going to stop a fire from happening south of town. It just might change fire behavior around that drainage so that it's less severe. There's a lot, so it's kind of comes down to, what are the objectives? And I think there's some misunderstanding that the objectives of that project are to reduce fires from happening or stop fire activity, or it's really to try to change the type of fire behavior if a fire occurs from a high severity fire to a lower severity fire. There's such an abundant dense conifer forest south of town that this project will not make a dent in all those fuels that are available, but it could make a fire a little bit easier to manage in the highlight watershed if that project were to go through.
Yeah. Okay. Well, so then I guess there's another question that comes in that I think really plays off of that, in your answer is, some people have argued that, one of the reasons we're having these mega fires is that we're not logging enough. Would any sort of mitigation protect against the mega fire, or? What are you thinking on that?
Yeah, and that's a great question. When we talk about fuel treatments, again, the all the science that you can find that looks at when you go manage a landscape, a forested landscape, you're really talking about, unless you remove every single fuel that's out there, you're really just talking about changing fire behavior, again, from a canopy fire to a surface fire. So there's quite robust data that shows that if you manage small diameter woody fuels, meaning remove shrubs and small trees, that you can change a fire's behavior from a canopy fire to a surface fire, which is much easier to manage and it's much less severe. The issue comes with a traditional commercial logging project is not targeting small diameter trees and saplings and shrubs. So there's a large disconnect between traditional logging and what we would talk about being a fuel treatment. Fuel treatments are really focused on small diameter, non-merchantable wood and shrubs. And so, that's a real challenging prospect for us. And there's a lot of folks looking at how can we make these small diameter trees and shrubs merchantable for wood chips or biomass burning, biomass plants or things like that. But a traditional logging project does not actually achieve the goals of a fuel treatment project. And I'll just bring up one example. In Oregon, on Weyerhaeuser and BLM land in 2020, one of the mega fires actually ran through recent clear cuts, thousands of acres of clear cuts, and it did not change the fire behavior in that system, that very productive system. And so, the idea that logging is going to, one, reduce fire activity, and two, actually change fire behavior, it's not well supported by the data. Whereas fuel treatments, removing small diameter trees and shrubs, it is supported in terms of changing fire behavior and making them easier to manage.
Okay, well, that's really interesting. So another question related to kind of the, this protection is, what about, the smoke? I mean, whether, a lot of times it's not even the fire in your community, it's the fire in the neighboring community and the smoke. And, how do we protect ourselves from that?
Yeah, that's a wicked problem. And one of the interesting lines of research that has been coming out just in the last couple of years is that prescribed fires, intentional fires during the cooler seasons has fewer harmful components in that smoke and less negative impacts on people. So the idea is that using prescribed fires to remove fuels under a much more manageable situation in the long run will reduce the amount of harmful smoke that we encounter across the West. It doesn't mean there won't be smoke. And, I think Missoula has been doing quite a few prescribed fires around the rattlesnake and the community. And they have quite an outreach program to talk to people about when prescribed fires are occurring and how to protect yourself from the moderate amount of smoke that is generated by those prescribed fires. So there's really no way to escape the impacts of smoke, other than we know that prescribed fires have produced less smoke and less harmful components than these really catastrophic mega fires. So we have to kind of think about these trade-offs of allowing ourselves to get used to a small level of smoke from prescribed fires versus the really big damaging fires that are the worst, can have the worst impacts on our air quality.
Right. Okay. Well, so another question is, how much of the current warming temperatures are caused by burning of fossil fuels and how much by natural cycles of the earth?
Yes, well, the model projections, and forgive me for being, I just haven't looked at this data recently, but I know that a majority of the warming is directly attributable to greenhouse gas emissions that are produced by humans. So most of the warming that we're seeing is caused by greenhouse gas emissions that from fossil fuels. And the reason we know that is because when we look at models that incorporate solar variability, sunspots, solar flares, volcanic eruptions, natural climate variability, they account for only a small percentage, a couple percent of the potential warming that can be attributable to natural climate variability. But a vast majority of the warming is directly attributable to fossil fuel, consumption. But I can't remember the numbers exactly, but it's a range, I think. But most of the warming is attributed to fossil fuel consumption.
Okay. Well, thank you for that. So another question that I guess, gets to the heart of, as I mentioned, this event is sponsored by INBRI, and, we're funded by the National Institutes of Health. And of course, so I have, some of my interest is in, public health and, what can be done. So are there things that, that public health organizations or the medical community can think about doing? If we know this is going to happen, well, do you have thoughts on what should we be thinking about doing?
Yeah, absolutely. And a lot of what I know about what's been discussed recently about what the health community or medical community and health community can do to help people deal with smoke and some of the negative impacts in air quality comes from the Rice Ridge fire that occurred a couple of years ago north of Missoula. A lot of folks got together and talked about what could be done, and they kind of talked with other folks in other states. And some of the most basic things are having community safe air quality places for people to go to. So city buildings, libraries, things like that. If people don't have high quality air filters in their homes or a way to escape the decrease in air quality, having places that they can go in the community and breathe clean air. That's one thing that has been discussed. And another is to distribute air filters to individuals that need them. Another project that I saw that looked really interesting was actually producing home air filters. If people, if things happen very quickly, there are actual things you can do to build an air filter at home out of some basic resources. And then just basic things about closing up your home. If you have an air system in your home, closing your windows and just doing some really basic things like that. But really making sure that all of the different populations in any given community have access to clean air during a smoke event. And I think that was what I saw was that it was a multifaceted approach, from providing public safe zones to distributing filters to helping people figure out what to do at home.
Okay. I have to say, you mentioned these filters that you can build, kind of the, DIY, do it yourself filters. Montana INBRI has just actually funded a project by a researcher at Montana Tech who's working on essentially really testing these do-it-yourself filters to come up with essentially a plan. And some of these filters, you use a room fan and $3 or $4 heater filters. And so for under $25, you can essentially build a filter system for your house and things.
Yeah, that's fantastic. I saw some summary of a project. It might have been that project.
Yeah, well, I think there's some YouTube videos too on some of that. But well, so a question that I think everybody was interested in that popped up here is, so what are the predictions for the 2021 fire season?
Yeah, Montana's a tough nut to crack in terms of predictions because, the first thing we look at is our snowpack. And obviously we had an extremely dry spate this winter where we had hardly any snow for a month, and then it kind of kicked in. And I think our snowpack levels are back up around 100% for most of the watersheds in Montana. But we can get lulled into this this kind of relying on snowpack to predict our fire seasons, and it's actually not a great predictor. And the reason is that we can have these flash droughts in Montana now, where all we need are 2 weeks of really hot, dry weather in August, and it really kind of overcomes even an unusually high snowpack season. So, I think I can't remember what year it was, but one year we had an extremely warm and dry March, and it really set up our fuels to dry out, and they continued to dry out, and we had a really bad fire season. But we've had other springs like that, and we have not had a lot of fires. So Montana is a little bit different from other states in the West in that it's very difficult to predict when we're going to have a bad fire season early on, this early in the spring. We just need some really hot, dry weather for a couple weeks, and we can all of a sudden jump from having an okay or very few fires to a lot of fires and a lot of big fires. So Montana is one of those really challenging states to predict the fire season far into the future.
Yeah.
I should say that, there've already been fires in eastern Montana this week. And there were fires in Alberta. So things are starting off, with quite a high level of fire activity early. But if we continue to get small rains that are evenly spaced throughout the summer, we could have a very moderate to low fire season. But we just can't predict. It's hard to predict here.
Yeah. Okay, and I can see that. The old saying, if you don't like the weather in Montana, well, wait a couple hours, it'll change.
That's right.
Yeah, so maybe we'll have one more question. And you mentioned this, the fire suppression that started in the 30s, and ecologists have been warning against this practice for decades. I mean, we've known that, but it's still going on in some areas. So how can science and scientists start having more influence on some of the management practices of federal land?
I think the best lesson that I've learned is from places where there's a culture of fire, like the southeastern United States. So if you live in Florida or parts of Louisiana and the Southeast, people are burning large landscapes every single year, and it's an accepted part of the culture. It's part of those ecosystems, and now people have accepted it as a positive process for both people and the ecosystems and in forestry and other purposes. And we have to somehow get back to a culture, learning from the way indigenous peoples used fire in Montana, and throughout the Western US, to it being part of our culture. I'm not sure how much of a role scientists can play in really, pushing that, but I think they can certainly present a lot of examples of how we used to use fire. And that's something that I'm really interested in, is looking at how indigenous peoples use fire, every year in Montana to promote resources that were beneficial to them and safeguard their communities. And of course, we know that ranchers in Montana use fire pretty in a savvy way to prepare ditches and croplands. And I think if we can get back to a nice mix of, fire is part of our culture, similar to how the southeastern communities are doing that. Obviously, different ecosystems, but bringing it as part of our culture, we can really have a much more positive future with fire. And I think scientists may play a small role in just providing examples of how that was done in the past.
All right. Well, I think that's a great spot to end, and a really, kind of positive outlook, and that's something that all of us in the community can do, is be a part of that. Just, it's not going to go away. So we're going to have to find a way to live with it, and let's make it, the best we can, given that fire is part of the natural process.
Yeah, and I will just add that, it'd be great if members of our community, these prescribed fire networks are growing in every state in the West, and including Montana. And I think if we can start to participate as citizens that care about our community in these prescribed fire networks, it would be a great way to get that culture back.
Yeah. All right. Well, Dave, I'd just like to thank you again, and welcome everybody else to do your virtual clapping. And thank you for just a wonderful talk, and, great Q&A session there. And thank you everybody who joined us this evening for this Cafe Scientifique. We will be holding these again in the fall, so please look for the announcements. And, we hope to join you again. And as I said, we may be back together in person in the fall. But thanks again for joining in, and have a wonderful evening.